am here to introduce resource person of this session, Dr. Sachin Bhalikar sir. Sachin Bhalikar sir worked as a professor at the School of Mathematical and Statistics, University of Hyderabad. He completed his Master of Science in 2007 and doctorate in mathematics in 2011 from the Department of Mathematics, University of Pune. His research interests are dynamics, system and fractional differential equations. He has published 73 research papers and he has more than 2,000, that is 2,159 Scopus citations. He worked on a 4th research project funded by NBHM, CSIR, UGC and SERB. He has published several research articles with international collaboration from USA, Turkey, Lebanon, etc. Under his guidance, 3 students have completed their PhD and presently 3 are working. He has received the Padma Shri-led N.S. Venkatesan Gold Medal for the Best PhD thesis in Mathematics from the University of Pune. He received the A.M. Mathai Research Excellence Award from the Society for Special Functions and their Applications in November 2018. He has been recognized as one of the top 2% highly cited scientists. He is an editor of a book entitled Frontiers in Fractional Calculus, published by Bentham Science in 2018. He has written several books, chapters in some of the reputed books. So it is my privilege to introduce such a dynamic personality. Now I request Sachin Bhalikar sir to continue the session. Sachin Bhalikar sir.
Good afternoon all. I'm happy to be here. First time in Lapur. So actually, even though I know Professor Vavre sir, and I can see so many familiar faces here after a long time, including Piyush Shroff sir. So it is indeed a great pleasure to deliver a talk in this conference. Okay. So in this talk we are going to discuss some discrete dynamical systems. So you all are familiar with differential equations. Okay, ODEs, PDEs kind of thing, and you know that these are very helpful in modeling natural phenomena. Okay, so starting from Newton's law of motion, we study in high school. Okay, so all these things are dynamical systems only. Now, in differential equations, whatever time variable we consider is continuous time. Okay, whenever we are writing y dash of t, then that t is usually a real number, or if we study some physical system, then that will be say positive real number kind of thing. Now, not all the processes we model with continuous time. For example, if it is a population, we don't measure population continuously. Instead, after some time instances. For example, if it is a bacteria population, we can measure say after 5 minutes. Okay, human population we measure after 10 years, such kind of thing. So this is discrete time. Okay, so here the title of talk is Dynamics of Fractional Order Discrete Dynamical System. So I will explain how fractional order is coming in picture. Okay, and what are applications. So this work is based on some collaborating project done with one physicist, Professor P.M. Gade from Nagpur University, and some of the students. Okay. So sequences you all are familiar with. Okay. So we study sequences from high school only. So sequences are nothing but these discrete time dynamical systems. Okay. So we study convergence of sequence in BSc Mathematics, or in MSc we study so many further properties of sequences. We also study sequences of functions. So all these things are nothing but discrete time systems. Okay. So equation of the form xn plus 1 equal to f of xn is very helpful in modeling natural systems. For example, if we consider xn plus 1 equal to r times xn into 1 minus xn, it is called as logistic map, and it is helpful in modeling population of single spaces. Okay. Now what is difference equation? Difference equation is an equation which contains difference operator. Okay, like we know what is differential equation. In differential equation there should be some term of the form y dash of x, y double dash of x kind of thing. Okay, so in difference equations we will need operators of the form delta y of n. So what is delta y of n? Here we define it to be y of n plus 1 minus y of n kind of thing. Okay, we may write it as y of n or y sub x n. It is the same thing. Okay. So here if we subtract xn from both sides, then this equation will become left hand side will be delta xn and right hand side will be f of xn minus xn, and if we call this as g of xn, then this will become your difference equation, equivalent to a sequence kind of thing. Okay. So this is part of dynamical systems, it is part of analysis, it is part of combinatory steps. Okay, so it is kind of interdisciplinary things, and applications are there in economics, physics, population dynamics, life science, and so on. So this is delta operator. In some cases we don't consider domain as natural number set. In that case, this h will appear. But to make the thing simpler, we will take h to be 1 and our domain to be natural number set union 0. Okay, so whatever our n or whatever our time, that will take the value 0, 1, 2, 3, 4 and so on. Okay. Now, why we need fractional order differences? Because we know if we consider this delta xn, then it will just take two values, xn plus 1 and xn. So there is no any inclusion of history, and we know that whenever we consider natural systems, then we always need history. Okay, what is meant by history here? History means the values from the starting point. Okay, so we know that past always affect our present, and whatever the things going on in present, this will surely affect future. Okay, so it is a non-local thing. Whatever real life problems, these are non-local problems. Okay, so we need some history, and it can be incorporated using non-integer order. Okay, so instead of taking delta square, delta cube of these functions, we need say delta power 0.7, delta power 3.5, such kind of things to model natural systems in a more appropriate ways. Okay, so these are some basic terminologies. So those who are quite familiar with fractional calculus, they will be able to relate these things with derivative and integrals. Okay, so whatever definition written in this slide, it is fractional order sum. Okay, so here sum means it is equivalent to integral operator. Okay, so it is defined using this thing delta power minus alpha x of t to be summation. There is a ratio of gamma functions and x of s. Note that here we take s from 0 to n. So we are considering x0, x1 up to xn. Okay, so all the history is coming in picture. That is the purpose here. Okay, we know that when we find the derivative at some point, then if you recall the first principle definition, then it will be limit h tends to 0, f of x plus h minus f of x kind of thing divided by h. So we just need the values of f near to the point x. Okay, so the ordinary derivative is a local operator. On the other hand, if you consider integral from 0 to 10 f of x, and if you recall trapezium rule or Simpson one-third rule, then you can see that we will need the values of function from the point 0 to 10. Okay, so all the points will be included. Similar kind of thing is there. So this is sum operator, and if you are familiar with gamma function, okay, even if you are not familiar, it is just generalization of factorial. Okay, we can take factorial of natural numbers, 5 factorial, 6 factorial kind of thing. But with gamma function, this can be extended to excuse me. Sorry. So we were talking about gamma. So we can extend that factorial things to real numbers, and not just real numbers, to complex numbers with some exceptions like -1, -2 and so on. Okay, so that this whatever ratio you can see here, it is nothing but generalization of binomial coefficient. Okay, you know what is NCR kind of thing you studied in 11th, 12th standard, or maybe before that. Okay, so NCR, when we are taking that is in that case n and r should be natural numbers. Okay, in this case it is generalization of that NCR. Okay, but here we are allowed to take alpha to be real number. Okay, so we need to use gamma. Okay, that's here we define difference of that. Okay, so again, those who are familiar with fractional calculus, they can relate this with definition of fractional derivative. Okay, we define fractional derivative using fractional integral. Similarly, here the non-integer order difference, okay, we can define using the fractional sum that we defined in previous slide. Okay, so if I am taking this mu between two integers, say 3 and 4, suppose my mu is between 3 and 4, so my m is 4. In that case, what I need to do, I am defining it like this. First I will take usual difference of order 4. So what is usual difference of order 4? We know delta f of x is f of n, say it will be f of n plus 1 minus f of n upon 1 kind of thing. Here we are taking x equal to 1. Similarly, we can have second order operator delta square f of n will be delta of f of n. Okay, and similarly we can generalize, and delta power n x of t we can give in terms of, we can use binomial theorem kind of thing. Okay, so binomial coefficients will be there mck minus 1 by 2 minus k x of t plus k, and k from 0 to x. So this we need to take first. So if our alpha is between say 3 to 4, then first I need to take order usual difference, and then I will take if my mu is 3.5, then this will be 4 minus 3.5, that is 0.5. Okay, so 0.5 order fractional sum, and that we are defining t. Okay, so these are the basic terms. Now when we are analyzing differential equations, we are using Laplace transform. Okay, Laplace transform not only helps in solving differential equations, but helps in analyzing the stability. We can find characteristic equation of linear differential equation with constant coefficients using Laplace transform, and then we can find the eigenvalues or characteristic roots, and based on their positions in complex plane, we can predicts solution behavior. For example, if the eigenvalues are in left half plane, that means real part is negative, in that case solution will tend to 0 as our time tends to infinity for differential equation case. Similarly, we can have analysis with difference equations, and in that case there is another transform which is called as Z transform, which can be applied to discrete functions, means sequences. Okay, so we are given a sequence n equal to 0 to infinity, or you may take n equal to some other value to infinity. Okay, in that case what is Z? It's Z transform. Either we denote it by capital letter Y, or we can write it as Z of Y, and we define it like summation y of k z power minus k from 0 to infinity. Okay, and we define this for those value, complex values z for which this series is absolutely convergent. Okay. Now, analogous to Laplace convolution, there is a convolution corresponding with Z transform. Okay, so how we define the convolution? Convolution is like this. We are having two discrete functions or two sequences phi and x. In that case, their convolution we define like this: phi of n minus s, x of s goes from 0 to n, and it is commutative kind of thing. Okay, we can interchange the order. We can write phi star x as x star phi. Okay, it can be easily verified. Now, Z transform of this convolution is product of their respective Z transforms. Now, this is generalized binomial function as we have seen, like NCR, n factorial upon r factorial n minus r factorial kind of thing. But in general sense, here alpha is real number, or we may take complex number also. So, notation is phi alpha tilde of n. It is gamma of n plus alpha minus 1 upon gamma of alpha gamma of n. So, it is nothing but minus 1 power n minus alpha choose n, or n plus alpha minus 1 choose n. Okay. So, Z transform of this thing is given by 1 upon 1 minus Z inverse power alpha, and it is valid for mod Z greater than 1. There are some computations behind this. If you take pen and paper and write down something, then you can arrive to these results. Okay. Now we consider this problem: fractional order difference equation, delta power alpha x of t equal to f of x of t plus alpha minus 1. Now we can see that why there is something like t plus alpha minus 1. Because the domains of delta power alpha are different than domain of delta square, etc. If you consider usual operator delta, then domain will be natural number. But here the domain of delta power alpha x is this set. It will contain 1 minus alpha, 2 minus alpha, 3 minus alpha, such set. Okay. And this is initial value x of 0 equal to x naught. Okay, so this system is equivalent to a sequence representation. Okay, so it is given by x of t equal to x0 plus this summation ratio of gamma functions and f of xj, z from 0 to t minus. Okay, now here we consider linear system in a higher dimension. So instead of function f, we can have a matrix. Okay, so it will look like this, or in more general sense, it will look like this. So our x t plus 1 will be a column vector equal to x0. It is a constant column vector, initial vector, plus a minus I is identity matrix, A is coefficient matrix, and this phi alpha tilde of t convolved with xt. Okay, so our problem reduced to this. Now we are going to find conditions for stability. Under what condition the solution will tend to 0. Okay. So we take Z transform of this thing. Now using basic rules of Z transform, we arrive to this equation. Okay, determinant of Z into 1 minus Z inverse power alpha into I minus A minus I equal to 0. Okay. So what is stability theorem? Stability theorem is the zero solution of our system, linear system, is asymptotically stable if all the roots of this equation, we can call these roots as eigenvalues, will satisfy the condition mod of that eigenvalue will be less than 1. Okay, so roots are z here, eigenvalues. Okay, so mod z should be less than 1. Okay, so if you put alpha equal to 1 here, then your condition will be reduced to our classical system. So our classical system will be xn plus 1 equal to axn kind of thing. Okay, so we are giving x0 and our x1 will be ax0, x2 will be ax1 and so on. Okay, for example, in one dimension, if you see xn plus 1 equal to axn, in that case solution, if you repeat the procedure, then x1 will be ax0, x2 will be ax1, but x1 is again ax0. So it will, in general, xn will be a power n x0. Now, what we want limit as n tends to infinity, xn should go to 0. So that is nothing but limit of a power n, and we know that limit of a is constant. Okay, limit of a power n will go to 0 under one condition. Are you familiar with that condition? BSc students will or MSc students will know that condition. Okay, so you have a sequence a square, a cube, a power 4 and so on, and you want this to go to 0. So what should be condition on a? Your a should be between -1 and n if it is a real number, and if you are taking a to be complex number, then your condition will be mod a less than 1, means that a should be inside unit circle in complex plane. Okay, so it should have distance from origin less than 1. Okay, so that is the same condition here if you put alpha equal to 1. Okay, and in that case it is eigenvalue of matrix A. Okay. Now, if our alpha is non-integer, finding all the roots of this equation determinant is not that simple. Okay, so there is one way what we can do. We can find the boundary of stable region in complex plane. Means what will be the condition for stability? Mod z less than 1. If our complex number z is of the form r e raised to I theta, then mod z less than 1 is the stable region. So boundary will be mod z equal to 1. Okay, so we will put z equal to e power I theta only. We are taking r equal to 1. R is nothing but absolute value of that complex number. Okay, so if we substitute z equal to e power I theta in that equation, then that equation reduced to a parametric curve in complex plane. What is parameter? Parameter is t here. Okay, so we will take t from 0 to 2 pi, and it looks complicated, but we need to use computer, and if we give particular value for alpha, it will generate some pictures. Okay, so the expression is like this. This is the real part and this is the imaginary part of that curve. Okay, so for each t, it will give a point in plane, complex plane. Okay, or here it is real part and imaginary part, so we can treat it as R2 plane. So the pictures are like this. If you put alpha equal to 1, then I just discussed what will be the stable region. Stable region will be unit circle, circle of radius 1 centered at origin. Okay, so if your eigenvalues of coefficient matrix are inside unit circle, your resulting solution will go to 0. On the other hand, if you take alpha less than 1, between 0 and 1, then that circle region is changed to cardioid kind of structure. Okay, so this is for alpha equal to 0.8, this is 0.6, 0.4 and this is 0.2. Okay, so whatever alpha we want, we can just put it here. Take our t between 0 to 2 pi, it will generate a curve. Okay, so we just have to check whether eigenvalues are inside. If all the eigenvalues are inside, it will generate stable solution. If at least one eigenvalue is outside this region, it will give unstable solution. Okay, we can check this with some examples. Okay. I will go to examples and come back to this. Okay, so here are some examples. Okay, so when these eigenvalues are outside, we are getting the unstable solutions, and for eigenvalues inside, we are getting this stable solution. Okay. I'm moving to one application. It is called as, how much time do I have? I will take one example from physics point of view. It is called as coupled mass lattices. These are appearing not only in physics but also in computer sciences, networks and so on. Okay. So here the systems are discrete again. X n plus 1 or xt plus 1 equal to a times xt, and there are some particular kind of matrices. This is circular matrix appearing in that coupled mass lattices, and there are a1, a2 and a0, three distinct values. We are going to take some particular values also. Okay, so here the capital N by N matrix. Okay, capital A is capital N by N matrix, and if your N is 2, it will look like this. Even if you take input 1, it will be 1 by 1 matrix of this form. Now, if matrix is circular, then there is a formula to find eigenvalues. Eigenvalues are given by, say, lambda L equal to A1 plus A2 omega raised to L plus A0 omega raised to minus L. Now, what is omega? Omega is that is nth root of unity, e raised to I 2 pi by capital N. Okay, this I is square root minus or usual thing. Okay, and if this matrix is symmetric, there is one case, it is called a symmetric case, when we take A2 equal to A0. In this case, these eigenvalues are like A1 plus 2 times A2 cos of theta L, and theta L is this one 2 pi L upon N. Okay, so we get real eigenvalues in this case when we take A2 equal to A0. And there is another case when we take A2 equal to minus A0. In that case, we have complex eigenvalues given by A1 plus I times 2 A2 sin theta L. Theta L is this way. Okay. So, if you consider this stable region, this was complex case. If our eigenvalues are real, then only points on this real line are important. Right endpoint is always 1, as you say. What about left endpoint? Left endpoint is 1 minus 2 power alpha, whatever your alpha means. So condition will be 1 minus 2 power alpha less than that real eigenvalue less than 1. In that case, solution will go to 2. Okay. So here is one example. We take 3 by 3 matrix, that circular matrix. We take alpha equal to 0.4 and other parameter values A0 is 0.2, A1 is minus 0.5, A2 equal to 0.5. This will produce eigenvalues minus 0.2, and these are minus 0.65 plus minus 0.086 I. Okay, so these are outside the stable region, we can say. Okay, so from previous figure, so minus 0.2 and okay, here we need to say one eigenvalue is minus 0.2 that is inside, but another value that is minus 0.65 plus or minus 0.08. Okay, so here alpha is 0.4. So alpha 0.4 means we need to refer to blue color curve. Okay, so that will be outside this region. And since it is outside, we are getting such solutions which are going away from 0. Okay, so oscillating and going away. On the other hand, in this case, if we take another set of parameters where inside that region, then we are getting such stable solutions. Okay. We can have some more particular cases, as we mentioned, that is symmetric case when we take A0 equal to A2. In that case, we can find stable region in the A1, A. There are two values only, either we can take A1, A2. Yeah. So in this parameter plane, we can find the region as quadrilateral. Okay. So these are the vertices containing alpha. Okay. So if our A1, there is a small proof. It is not that difficult. Some simple mathematical calculations will be there, and you can easily understand it. So I am not going to discuss all these details, but it will come like this. Okay, so this will be our stable region depending on your alpha. If you give particular value of alpha, you can find that quadrilateral. Okay, so if this is in A1, A2 plane, Note that this is not complex plane. Earlier structure was in complex plane. Here, whatever parameters, we can just check whether parameters are inside or outside. So, on the other hand, if we consider another case, that is a symmetric case, then we will have different set of parameters and we will have different result. Okay. So here is the example when we take capital N to be 8 and alpha equal to 0.2. In that case, the region looks like this. And this is the example. So first we take A1 equal to 0.1, A2 equal to minus 0.05. 0.1 is here somewhere. Okay. A1 and A2 is minus 0.05. So it will be point here somewhere inside. Okay. So it is inside and the solutions are like this, going slowly to 0. Okay. On the other hand, if we take this point A1 minus 0.02, A2 equal to 0.1. Okay. So it will be here somewhere outside the region, and in that case we are getting unstable solution. And similarly, we will consider another set of parameters, verify it. Okay, and this is the case which is called as the symmetric case, A0 equal to minus A2. In this case, we don't get that quadrilateral type region. Instead, our stable region after these computations we get like this, not a cardioid again, but it will be part of cardioid. So there is one line that is A1 equal to 1. This is in the A1 equivalent, not in complex plane. Okay. So A1 equal to 1 is the right boundary. Beyond that, we don't get stable solutions. Okay. This is also verified with some examples. All these results are proved using whatever mathematical analysis. Okay. So, and this is particular example where we verify. Okay. So we use Z transform to carry out these computations, and we analyze the stability. We used Fortran language and Mathematica software to do this. Further, we worked on some complex order cases also. When alpha is a complex number, we provided mathematical analysis in that case, and few more interesting things like periodic math lattices. We also worked on chaos synchronization, like structures in these maps. Okay. So I think I should stop here because it is a long time also. But anyway, whatever your doubts you can ask me. If you find it interesting, then these papers are also available online, and I will share this PDF file with coordinators and you can read it. If there is anything to discuss, you can. If there is any suggestion or whatever you are doing. And then we can start.
Thank you very much, sir, for an enlightening and insightful lecture. Now, the respected chairman of this technical session, Dr. Commander sir, is requested to kindly present chairman's remark and share reflection on this.
I think this session is wonderful session, and so let's start with very basic thing. What is difference equation? Because I am not from mathematics background. I left mathematics in the BSc, but till today I understood the whole thing what they are explaining here. So without mathematics background, if I understood, I think whole audience gets the things what they want to say. This presentation extends the traditional difference equation to fractional order concepts, valuable for modeling systems with memories such as those found in economics and biology. The core of talk focus on stability analysis of these new systems using set transform as a key mathematical tool. The presenter establishes a critical stability criteria. A system is stable only if all roots of its characteristics equation lie within a specific cardiac shaped region which varies with the fractional order. This theory is then applied to coupled map lattice, that is CMLS, which are network of interacting maps. Also, sir has explained one example from physics side. I think I'm here in the mathematics lecture, but I got some knowledge from the physics also, how that CMLS is applied in the physics also. The presentation analyzes two spatial coupling configuration, deriving the precise condition on system parameters like coupling strength that guarantee stability. It is shown that the stability region depends on the number of lattice points and whether the coupling is symmetric. In conclusion, the set transform proves to be an effective method for stability analysis. The finding provide a framework for understanding both linear and non-linear fractional systems. With the stability of non-linear systems, equilibrium points being determined by the eigenvalues of its linearized forms. These are some concluding remarks from my side. So with this, I thankful to the resource person of this session for giving such a wonderful lecture over here, and also I am thankful from my side as well as from the conference organizer's side for giving such a wonderful lecture here. Thanks.
Thank you, sir, for the valuable remarks and observations. Sincere thanks are extended to Dr. Sachin Bhalekar, sir, for delivering such an inspiring and informative lecture and for sharing his expertise with all the participants. With this, technical session 7 comes to a successful conclusion. Gratitude is extended to the respected chair, resource person, and all the participants for their presence and engagement. After this, we will have a lunch break. We will gather here at 2 p.m. sharply.
All the participants are here requested, whoever is wishing to give the feedback on this conference, they should submit their